All right, section 4.1 is inverse functions, and you should already have an idea of what inverse functions are, functions that undo each other. When you very first started solving equations, I'm sure that the teacher didn't use the word inverse functions, but really you were doing it when you realized that if you had x plus 2 equals 7, to unadd, you have to subtract because addition and subtraction are inverses of each other. When you had 3x equals 10, you had to divide both sides by 3 because multiplication and division are inverses of each other. So inverse functions just undo each other. You can think of them as being a two-part machine, that if you take an x and put it in the first part of the machine, it spits out a y. But if you take out that y and put it into the second machine, it will spit back out your original x because the two functions are undoing each other. Think of an inverse function as an undoing machine. The inverse of a function undoes what the original function does. For example, if f of x is an adding 2 machine, then a function g of x, a subtracting 2 machine, would be its inverse. Or if f of x is a doubling machine, then g of x, a halving machine, would be its inverse. However, for the inverse of a function to exist, it must be 1-to-1. That is, for each y, there must correspond only one x, so that the inverse function can return an original unique value. Now, how could we tell by looking at a graph if a function was if a relation was a function? The vertical line test. If it failed the vertical line test, that would mean that there was one x, at least one x, that had two different y values, and that's why the function failed the vertical line test. Well, one-to-oneness goes one step beyond that. We've said that y equals x squared is a function because it passes the vertical line test. It's a parabola, and a concave up parabola would pass the vertical line test. However, now we're going to say, yes, it is a function, but it's not 1-to-1 because there is one y value that has two different x values. It is a function. It does pass the vertical line test, but it doesn't pass, we could call this the horizontal line test. Therefore, the function is not 1-to-1. If you put the number -3 into a squaring machine, that squaring machine would spit out a 9. But if you took that 9 and put it in a square rooting machine, then the square rooting machine is going to start smoking and worrying about, was the original number a 3 or a -3? Because it could have been either one. If you put a 9 into a square root machine and say, find the square root, 9 has two square roots, +3 and -3. So x squared is a function, but it's not a 1-to-1 function. And in order for a function's inverse to be defined, then the function has to be 1-to-1 so that the inverse function knows what original value to give back. The definition of a function is a relation for which each distinct x, there corresponds one and only one y in the range. The definition of a 1-to-1 function just goes one step beyond that. Not only is it true that for each x there's only one y, but it's also true that for each y there's only one x. Here's the example that I've been talking about, y equals x squared. If we look at the two elements in the domain of that function, -2 and +2, each one only corresponds to one y. If you square -2, there's only one right answer. If you square +2, there's only one right answer. Therefore, that is a function. However, it's not a 1-to-1 function because two different x's give you the same y. All right, to prove that a function is 1-to-1, you must show that if two y values are equal, they came from two equivalent x values. To prove that something's not 1-to-1, you only have to find one example for which two different x's generate the same y. In math, it's a lot easier to prove that something is not true than it is to prove that it is true. To prove that it's not true, all you have to do is provide one example where it's not true. To prove that something is true, you have to prove it's true for all real numbers, and sometimes that's much harder. In this case, it's not a whole lot harder, but let me show you some examples. This is page 258. And number 4 just gives you part A, B, and C, 3 different graphs. First, tell whether the graph represents a function, and then if it does, tell whether the graph represents a 1-to-1 function. What about the A part? Is that a function? Yes, it passes the vertical line test. For each x, there's only one corresponding height on the graph. Is it a 1-to-1 function? No, it fails the vertical line test. Right here you have 3 different x's that all have the same height. So that is a function, but it's not 1-to-1. What about B? Is that a function? Yes. Is it a 1-to-1 function? Yes. No matter where you put a vertical line or a horizontal line, it would only touch that graph in one place. What about C? Is it a function? It's not even a function. Can't be a 1-to-1 function because it's not even a function. It fails the vertical line test. Here's one x that has 2 different heights. So that's not a function. 5 through 16 say determine whether the function is 1-to-1. Well, let's do number 6. $258. No, we want to formally prove, not just prove by example. You can't prove something is true by example because there might be another example for which it's not true. And really, a graph is not a formal proof. You can tell by looking at the graph, but that's not considered a proof. Anytime the directions say determine whether the function is 1-to-1, first get a gut feeling of whether that's 1-to-1. Could you think of 2 different x values that would give you the same y value here? I don't think so. I think for every x, you're going to get a different y. And of course, when you let x be 2, the whole thing's going to be undefined. But for every other x in the whole wide world, there's going to be a unique y value. So I think it is 1-to-1. But saying I think it is doesn't prove it is. So to show that it is 1-to-1, we need to show that if f of A equals f of B, that means if 2 y values are the same, the only way that can happen is if the 2 x's you put in are the same. Now, we're not going to do very many proofs this semester. We'll do some when we get to trig, but all proofs start with a statement of what you're trying to prove. This is what we're trying to prove, and then you have to start with a given, and from that given, work your way to the conclusion. What we're given here is that f of A equals f of B, and we want to see if that proves that A has to equal B. Well, how do you find f of A? What does that mean? Put A in the place of x, 1 over A minus 2. What's f of B? 1 over b minus 2. We're trying to find out if this statement is equivalent to A has to equal B. So this is a proportion. We could cross multiply or multiply both sides by the LCD to clear out fractions. That would be the same thing. If we just cross multiply, we have B minus 2 equals A minus 2. And what could we do to both sides to be left with A equals B? Just add 2 to both sides. So we have proven that the only way these two expressions can be equivalent is if your two x values are equivalent. That proves one-to-oneness. Now, I like to end all of my proofs with voila. But that's not the official way to end a proof. It's just my personal favorite. The official end to this proof would be, therefore, f of x is, just state what you set out to prove. You set out to prove that f of x is 1-to-1, and sure enough it is. Because if f of A equals f of B, then B has to equal A. All right. What about number 8? F of x equals x squared plus 3. Before you embark on this whole journey of a proof, see what your gut thinks. Do you think that's 1-to-1? Can you think of two different x values that would give you the same y value? Give me an example. 3 and negative 3 would give you the same y value. To prove something's not 1-to-1 doesn't require a proof at all. You just have to give one example of two different x's that give you the same y. So I'm just going to say that this is not 1-to-1. An example of why it's not 1-to-1 is that f of 3 equals f of negative 3. They both give you 6. No, they don't. No, they don't give you 6. I just said 3 plus 3 instead of 9 plus 3. So that's two different x's. That correspond to the same y value. Now, I'm not going to write down another proof like this. There is another good one in the book. I think it's example 1 if you need to see another one. But even without writing it down, number 10 is probably even easier than number 6. If you write your whole, show that if f of A equals f of B, then A has to equal B. But when you get down to the proof, what is f of A going to be? Cube root of A, f of B is going to be cube root of B. And if you had cube root of A equals cube root of B, what could you do to both sides to end up with just A equals B? Just cube both sides. And so you would have proven that that's 1-to-1. What does your gut say about number 12? Is that 1 to 1? Every x in the whole wide world is going to have the same y value in number 12. So it's definitely not 1 to 1. All you have to do is give one example. F of 0 is 3 and f of 1 is 3. So that's two different x's that have the same y. What does your gut say about number 14? 1 to 1 or not 1 to 1? Give me an example of two different x's that if you cube them, you get the same y. Do you get the same y value for, say, positive 1 and negative 1? No? I think that is 1 to 1. Because every distinct x is going to give you one distinct y. No two x's are going to give you the same y. If you think about what you know about the graph of x cubed, it's that vertical snake-shaped graph. It passes the horizontal line test. So that's 1 to 1. What about number 16? Would you think that's 1 to 1? Nothing with an x square in it's going to be 1 to 1 because a number and its opposite have the same square. All right, that's in the homework you do 3 through 15. So we've talked about that. Let's see. Vertical and horizontal line test. Well, I must have skipped ahead. We already talked about that, and we've already looked at problem number 3. So what about the theorem on increasing or decreasing functions? I didn't bring that page with me, but all that theorem says is that if you have functions that are either increasing throughout their entire domain or decreasing throughout their entire domain, then they're automatically 1 to 1. Because think about what a function that's increasing throughout its entire domain looks like. Maybe the cube function. It's forever increasing. It's never going to double back. And if it never doubles back, it's 1 to 1. And the same thing for a function that's decreasing. It's always decreasing and never doubles back, then that function's 1 to 1. All right, the official definition of an inverse function is a lot of fun. Let f be a 1 to 1 function with domain D and range R. Domain D is just the set of all numbers that you can let x be, all numbers for which the function is defined. The range R is just the set of all possible y values that can be obtained from that function. A function G that has domain R, all the same numbers that were in the range of the original function, and range D, all the functions that were in the domain of the original function. If you have such a function, then G is the inverse of f if and only if you put x into the function f and get out a y, you should be able to put that y into the function g and get back out your original x. Now that makes more sense the way, or hopefully makes more sense the way I said it than the way it has to be written officially in a math book. But if you want to prove that f and g are inverses of each other, you just need to show that if you put an x into the function f, the machine f, and it spits out a y, and then you take that y and put it into g, if it gives you back the original x, then f and g are inverses of each other. For example, f of x equals 4x, a quadrupling function. If g of x is 1/4 x, which is a quartering function, What do you get if you put 7 into the quadrupling machine? 28. If you take that 28 and put it into the quartering machine, what do you get back? The original 7. Therefore, F and G are inverses of each other. All right. Back to this page 1 second. Notice here that if you put a 7 in place of X and get out a 28, that means that the ordered pair 428 is on the graph of F of X. You put 4 into the function F, you get out a 28. That means the ordered pair 428 is on the graph of that function. If you take that 28 and put it into the quartering machine and it spits back out a, wait. Why don't y'all stop me when I make a mistake? I'm supposed to put 7 into the quartering machine and get out a 28. Put 7 into the quadrupling machine and get out a 28. When I put a 28 into the quartering machine, I get back out this original 7. So the ordered pair 28, 7 is on the graph of G of X. Since I messed that one up a little bit, let's think about if we let X be 3. If we let X be 3 and put it into the quadrupling machine, we'd get out a 12. That means the point 312 is on the graph of F of X. Then if we put 12 into the quartering machine and got out a 3, that would mean the ordered pair 12, 3 is on the graph of G of X. In other words, all of the ordered pairs that are on F of X, all of the ordered pair XY, come back as ordered pairs YX on the graph of the function. Has all the same ordered pairs, but with the X and Y interchanged. And that is what is at the top of the next page. If AB is on the graph of F, then BA will be on the graph of G. Therefore, the graphs of F and G are reflections of each other through the line y equals x. If you think about the function x cubed, what is the inverse of x cubed? No, not opposite of x cubed. Cube root of x. What undoes x cubed? Cube root of x. And you know what the cube root of x looks like is that sideways snake. Well, those two graphs, I'm sorry if y'all didn't bring colored pencils with you today, but those two graphs are reflections of each other along the line y equals x. That green line is the line y equals x. And the blue one is y equals cube root of x. And all of the ordered pairs that are on the black function are just reversed to give you the blue function. It's inverse. Now, math, all the rules of math, all the symbols of math are very carefully defined so that you don't have one symbol meaning two different things. Hardly ever do you have one symbol that can mean two different things. But somebody slipped up on inverse functions. When you see, for example, x to the negative 1, what does that mean? 1 over x. That's how you make an exponent positive. You take the reciprocal of the base, and that makes the exponent positive. Well, here's what somebody decided to use for the notation for the inverse function. It looks like f to the negative 1, but it is not f to the negative 1. It bothers me that in math you have what looks like an exponent of negative 1 meaning two different things. If you write x to the negative 1, that does mean 1 over x, but if you ever see f to the negative 1 or a function to what looks like the negative 1, don't even read it as to the negative 1. If you read it to the negative 1, you'll misunderstand it. Just when you see that symbol, read it as the inverse of f. There's f and then f inverse. Not to be confused with the reciprocal function. All right. The theorem on inverse functions is on page 252, but I've rewritten it in terms that work pretty well and make sense. The theorem on inverse functions just says that if you form the composite function f of g of x, then f and g undo each other and just leave you x. If you form the composite function g of f of x, they undo each other and just leave you x. By the definition of inverse, functions that undo each other, if you form the composite function, either f of g of x or g of f of x, they should undo each other and just leave you x. That's how you actually prove, not just illustrate, but prove that two functions are inverses of each other. I notice two parentheses that are missing right here. G of f of x and f of g of x. I have two opening parentheses that didn't have a closing parenthesis. All right, look at the example I typed, and then I'll do another one like this. Number 20 says, use the theorem on inverse functions to prove that f and g are inverse functions of each other and sketch f and g on the same coordinate plane. Just like we did x cubed and cube root of x, sketch them both on the same graph so that you can see one is just the reflection of the other along the line y equals x. All right, the fact that it says prove means we're doing a formal proof here. Here's my show that statement. I said all proofs have a show that statement, and if you're trying to prove f and g are inverses of each other, you have to show that the composite function f of g of x simplifies to just x, and the function g of f of x simplifies to just x. Well, let's go back and look at these two original functions for a second, and then we'll do the proof. If f of x is x squared plus 5, I thought we just said anything with an x squared in it, it's not 1 to 1. And if it's not 1 to 1, then you can't find its inverse. We said that, right? Because this would be a concave up parabola shifted up 5 units. It wouldn't pass the 1 to 1 test. But if you wanted to, you could use a restricted domain, just part of the domain of that function, and then you would have a 1-to-1 function over just that part of its domain. So if I just say for all the x's less than 0, y is x squared plus 5, then I just have the left half of that parabola, And if I'm only using the left half of that parabola, then it is 1 to 1. So the only reason f of x, the only reason we can find the inverse for f of x is that we were given a restricted domain. If we hadn't been given that, we'd just have to say, can't find the inverse of f, it's not 1 to 1. All right, g of x, what's the square root of x look like? What's the graph? It's half a parabola. As a matter of fact, g of x equals negative square root of x. That's the bottom half of a parabola. This would be a parabola shifted 5 units to the right. Bottom half of a parabola that's been shifted 5 units to the right. Here's the line y equals x that bisects the first and third quadrants. If I fold this paper in half along that dashed line, does it look like the two graphs would match up? You can no longer see. But does it look like they would? Yeah. So my graph tells me and my gut tells me that if we restrict the domain of f of x, then we do have, or we are able to find the inverse of this function, and it will be this function. This function has the ordered pair 0, 5. This function has the ordered pair 5, 0. All of the other points on these two graphs would just be the same with the x and y exchanged. So I've looked at the graph. Now let's actually do this proof. Show that f of g of x equals x. How do you find the composite function f of g of x? Take g of x, whatever it is, and put it into f. Well, g of x is negative square root of x minus 5. Take that and put it in the place of both of those x's. Here's what you would have. Oh, there's not a both of those x's. That x is part of the restricted domain. Just x squared plus 5. Put g of x in the place of x. When you square negative square root of x minus 5, you just get x minus 5 because a negative squared is a positive. So that's x minus 5, and if you add that 5, they undo each other and just leave you the x. You just have to prove that this works both ways. Not only is f of g of x, x, but you also have to prove that g of f of x leaves you just x. So take f of x, which is x squared plus 5, put it in place of this x right here, and you'll have negative square root of x squared plus 5 minus 5. The plus 5 and minus 5 give you 0, so you have negative square root of x squared. If x is a negative number, this is what this note pertains to. If you put in a negative x value and square it and then take the square root, do you get out the same negative that you put in? Think about if you put negative 3 into the squaring machine, what do you get? 9, and then if you take the square root of 9, you don't get back the same x that you put in. You get its opposite. You get out a negative 3. So negative square root of x squared, if x is a negative number, you don't get out what you put in. You get the opposite of what you put in. And then that negative in front of the radical, and those two undo each other and just leave you x. I typed the hardest problem so you could just listen. Most of them aren't this hard. But you really have to think about, we're tempted to say square root of x squared is just x. but that's not true. If you put in a negative number, you don't get back out that same negative number. You get the opposite of what you put in. And so this is this negative I'm just keeping up with, and this is negative x because we're only using negative numbers for x. Right, so you didn't get back out the same thing you put in. You put in a negative 2, but you got out a positive 2. So you got out not what you put in, but the opposite of what you put in. And that's why I'm saying the square root of x squared isn't x, it's the opposite of x if you're putting in negative numbers. All right, we have time, I think, to do one more of these just to convince you that the only thing that makes this one hard is that domain issue, and square root of x squared is not just x. Let me show you another one that's not that difficult. Number 20, let's see. 19, these problems all have the same directions, 19 through 22. So let's look at 22. You have f of x equals x cubed minus 4, and g of x equals cube root of x plus 4. By the way, these problems say sketch f and g on the same graph. Graph them on your calculator and then just copy the graph on your paper, just like I have done here and here. Show f of x and g of x and their reflections of each other along the line y equals x. All right, so 22, I'm not going to think about the graph just so we can finish this one. If I told you that I was going to build a machine that cubed any x that you put in and then subtracted 4, what would a machine that undoes that have to do? Let me say that one more time. My machine does two things. It cubes whatever you put in and then subtracts 4. If you wanted to undo that, what would you have to do? Add 4 and then take the cube root. So my gut tells me these are inverses of each other, but to actually show that they are inverses of each other, I need to show that f of x put into the function g leaves me just x, and f of g of x leaves me just x. Well, what is g of f of x? What does that mean? Take f, whatever it is, and put it in place of x in the function g. That means put x cubed minus 4 in the place of x, and I'm only using parentheses so that you can see that whole thing is in place of this x. The parentheses aren't really necessary. And g of x also takes that x and then adds 4. Well, that would be just the cube root of x cubed, because the minus 4 plus 4 gives you 0. Is it true that whether you take a negative or a positive, if you cube it, or really raise to any odd power, and then take that same odd root, is it true that you're always going to get back what you put in? Yeah, with odd powers, yes. If you put in a positive 2, you get 8, and then take the cube root, you get back that same positive 2. If you put in a negative 2 and cube it, you get negative 8. Take the cube root, you get back the same negative 2. So we don't have to worry about a domain issue on this one. Cube root of x cubed is just x. So we've done the first part of the proof. Now we need to prove that f of g of x gives us back our original x as well. So take g of x, cube root of x plus 4, put it in place of this x. Cube root of x plus 4 cubed minus 4. What's the cube root of x plus 4 cubed? Just x plus 4. So you have x plus 4 minus 4, and sure enough, that's just x. You've proven that the two functions undo each other. If you're a stick in the mud, you can say, therefore, f of x and g of x are inverses of each other. All right, so in 20 and 22, we were given two functions and asked to prove that they were inverses of each other, and we did. But 27 through 48 say find the inverse function. We're given a function f of x, and we have to find its inverse. Look at the one I have typed, and then maybe we'll have time to do one more. Here are the steps. I typed them out for you because you need to know what I've done in each step. To find if f of x equals 4x over x minus 2, and you want to find its inverse function or its undoing function, the previous problem, it was easy to figure out if I'm going to build a machine that cubes a number and then subtracts 4, the undoing machine would need to add 4, then take the cube root. That was pretty easy to figure out. This one's not as easy to say. If I'm going to build a machine f that quadruples a number and then divides it by 2 less than the number, my brain just exploded. And I can't say what the undoing machine needs to do. So here's how to find the inverse if you can't just talk yourself through it. Put y in the place of f of x, and then just solve for x. Get that x by itself. You would have to clear out the fractions, multiply both sides by x minus 2, and then you'd have to clear the parentheses. If you're solving for x, the next step would be get all the terms with an x on one side, all the terms without an x on the other. And then because x is part of two terms you can't combine, the only way you're going to be able to get that x by itself is to factor it out and then divide by the stuff that's left. Now we have x as a function of y, but when you write the inverse function, you want x to still be the independent variable. So the last step in all of these problems are just interchange your x's and y's. Your inverse function is 2x over x minus 4. That's the machine that would undo this machine. Maybe I could have talked myself into that. I don't think so. Maybe some of you could. Some of you that are capable of keeping more in your head at once than I am, maybe you could have figured that out. In the time it would have taken me to figure that out, I could have just written it down and found the inverse function much faster. All right. In the book, there's a guideline 3 that says show that the domain of f is the range of g and the domain of g is the range of f. don't worry about that. Just find the inverse function. So let's do one more using these same steps. 32, any, mini, miny, mo, do I have a favorite? Let's do 42. I was trying to see if any of them had some special odd trick, but I think 32 might be the hardest one. I think I could find that inverse function in my head. If you told me you were going to build a machine that took any x, cubed it, added 1, and then raised that to the 5th power, I can work through that process backwards. The inverse function is going to have to take the 5th root and then subtract 1 and then take the cube root. But let's say I can't do that in my head either and actually find the inverse. Using the same steps as the previous page, I'm going to put y in the place of f of x. And then solve that for x. What's the first thing I'd have to do? Fifth root of y would just be x cubed plus 1. Then what? Something before that. Before I can take the cube root of this right-hand side, if I took the cube root of x plus 1, I couldn't simplify that. But if I subtract 1 from both sides, then I could take the cube root of both sides. That left-hand side would just be ugly. I'd have a 5th root under a cube root. I wrote the right thing. I think I might have said the wrong thing. Yeah. No, that was right. 5th root under a cube root. That was right. And so the inverse of f, not to be confused with the reciprocal of f, just interchange the x's and y's here. F inverse would be cube root of 5th root of x minus 1. Have we ever finished 2 minutes early and we're not behind? Never! That's so awesome. Okie doke. Homework is at the bottom of the page, 3 through 15 odd, 19, 27 through 33 odd.